Hey everybody, so this research paper is called A Mean Field Theory of Theta Expectations. And this paper is like 100% math, like 100%. So I'll dive into a few things in this research paper specifically, and then I'll dive into like why exactly this research paper matters overall, right? So the abstract is pretty dry. The canonical theory of sublinear expectations, a foundation of stochastic calculus under ambiguity, is insensitive to the non-convex geometry of primitive uncertainty models. This paper develops a new stochastic calculus for a structured class of non-convex models. We introduce a class of fully coupled mean field forward backward stochastic differential equations where the BSDE driver is defined by a pointwise maximization over a law-dependent non-convex set. I'm going to stop here. I 1,000,000% understand why there are not a lot of people that get into this. I get it. This is dry. This is dense. The whole entire paper is so like there's we go into what I would want to get into within this, right, which is like application, right? Like what's the actual application? The actual application is more math, like more and more and more math, and then we go down here to the there's a paragraph. So the resulting dynamics are fundamentally different. The theta calculus captures the bimodal nature of the agent's belief, forcing a discrete choice between distinct regimes. The sublinear framework, by convexifying the uncertainty set, erases this structure and leads to an average dynamic that does not correspond to any of the originally conceived regimes. Our theory thus resolves the identifiability impasse by providing a valuation that is sensitive to the fine-grained non-convex geometry of the primitive model set. Again, very dry within this, right? So why exactly am I talking about this? What exactly is this talking about? This is all related to P-Faf. My P-Faf research is why I'm bringing this up very specifically. And then so what they're talking about with this calculus problem is what I've been talking about for 3 years with P-Faf to anyone that would listen around it, right? And so here it is, a full-on mathematician explaining these exact same concepts to you in very pure mathematical terms. 42 pages of pure math. If you are interested in this subject from a purely mathematical standpoint. If you're not, let's break this down into more simplistic terms. All of this boils down to essentially what we currently have with the tokenization mechanisms, right? And the basis, the core structure of tokenization mechanisms is a process called seek-to-seek, SEQ to SEQ. And then that process is been around since like the mid 2010s, and then essentially the process like seek to seek over mid 2000s, and then seek to seek overall is the driving mechanism for tokenization. It's a linear algebra based process, and then the reason why it's like a linear algebra based process as opposed to a calculus based process is exactly what they're talking about here within this research paper is that there's not a way to define and get what you need out of these things with standard calculus. These are all things that I ran into with P-Faf, right? And then a lot of people that don't understand these things were the criticism were like, how would someone like me figure these things out? And it's, if you look at these things from an engineering perspective, and I have access to let's say Wolfram GPT, for example, I don't necessarily need to be on this same level mathematically in order to understand the core mathematical concepts. I love math overall. Math to me overall is based off of logic, right? It's a subset of logic overall. And then so as long as you frame it and you look at it from that perspective, math is very elegant. And what it does, it solves problems, right? It's an engineering problem for like code. It's engineering around problems, and you can create efficiencies and different tools and things like that out of math overall, right? That's exactly how I look at it. And then so that's exactly how I looked at it and look at it in this sense overall, and why and how essentially P-Faf came about within this exact equation. Like I went through the exact same process that this research paper is going through, solving this exact same problem, right? This linear calculus based problem when it comes to essentially tokenization of the models. And then so giving you like the crystal clear what's the actual impact of this. Like this is a better seek-to-seek, a better tokenization process overall is the best way that I could describe it, right? It's a more probabilistic tokenization process. And then they solve this problem a little bit differently than I do within that, like, but mathematically, but it's the same exact concept, which is overall that tokenization in and of itself is lossy. I've gone over this before, right? So if we accept that and we acknowledge that, then we can acknowledge that we don't need to have 100% linearity. Like we can sacrifice some linearity within that equation for probability. We don't want to sacrifice a lot, obviously, but we have room to play within that. Like it doesn't have to follow like the typical it's going to be 100% linear algebra, right? Like it's just because like seek to seek is 100% linear algebra, but it's not, it's lossy in and of itself, right? Like all we have to do is be less lossy than seek to seek. Which isn't hard within that math, right? So as long as you come at it from that perspective, you realize that you can sacrifice some level of accuracy for probability, and then within that gives you a lever to play around with, and then you can utilize calculus, which like you want to utilize calculus within these equations, right? But that like so that gets you access. It's kind of the gateway, the door in between these two models, right? And then so to like make this clear with regards and tying this directly to this research paper here very specifically, I had ChatGPT come up with this. So TLDR, the paper is like saying traditional systems make decisions by averaging things out, but in real life, uncertainty isn't smooth or nicely shaped. It's messy. So we built a new system that understands and works with messy uncertainty. And PFAF is your answer to the same problem, but inside of a neural network. This is what they're saying. PFAF is doing the same thing overall, which is why it caught my eye very specifically, right? So what's the problem? Traditional models are too quote unquote safe. Most AI systems today assume that uncertainty, things we're unsure about, behaves like a nice round shape, like a circle or a balloon. These models are smooth and predictable, but they oversimplify reality. Example, imagine trying to describe the shape of a mountain range using only perfect spheres. You miss all of the valleys, peaks, and cliffs. The paper says if the real world is jagged and weirdly shaped, we need tools that can handle jagged and weird uncertainty. If you know anything about the math behind these things, it's always poincaré balls, except like spherical shapes, etc. Right? And then within that geometry smoothing is that's lost, right? And then so if we can make it more jagged, it's less lossy overall. Right? It's kind of the concept behind that, the way that I look at it. So what's the new idea in the paper? Theta expectation. They created something called theta expectation, a new way to process information without pretending that things are smooth. Instead of assuming uncertainty is always a nice shape, it says, let's work with the actual messy shape of uncertainty, even if it's spiky, split, or full of holes. This allows the model to react differently to different situations, depending on the actual structure of the data, not just the average. So what's P-Faf doing that's similar? My P-Faf activation function. P-Faf is a brain-like switch inside of neural networks that doesn't just look at input values. It looks at patterns and at textures in the data like a fractal would. So instead of a boring yes-no switch, like if input, then 0, activate, P-Faf says, let me feel the local structure, the noise, the chaos, and then probabilistically decide how to activate. This is a non-smooth, adaptive, and context-aware function. It thrives in messy spaces, just like the theta expectation framework. So side-by-side comparison, core idea of the theta expectation paper is work with real-world messy uncertainty. PFAF handles complex, noisy patterns and data natively. The target for the Theta paper is financial risk, systems with ambiguous choices. PFAF is neural network decision-making and representations. The rejections are, for the theta expectations, are convexity, smooth uncertainty sets, and then for PFAF, it's simple fixed activation functions like ReLU. why this all matters. For the Theta paper, it's better decisions and uncertain real-world systems. For PFAF, it's smarter neural networks that respond to data structure. Why should a non-expert care? Both the paper and PFAF tells us that the real world is full of uncertainty and most tools oversimplify it. If you're a trader, therapist, engineer, or game designer, your decisions involve uncertainty that isn't smooth. Tools like data expectation and P-Faf don't round off the edges. They embrace the weirdness, helping AI understand noise and decision-making more like humans do. So the technical bridge, if someone wants kind of like a soft technical metaphor, data expectation is like navigating a forest using a topographic map that shows every ridge and valley, not just a flat aerial view. PFAF is like a robot that changes how it walks based on the bumps under its feet. It doesn't just go on off, it listens to the ground texture. And so these concepts are in the same realm, in this same playground, dealing with these same exact concepts, right? And then so again, I get it's easy if you don't understand these things or in these realms, like this guy's just coming up with like this wild, crazy stuff out of nowhere, right? I guarantee you that's not the case within this, right? It's very specifically going through and understanding these things from an engineering perspective, and then understanding enough of the math behind these things in order to do these things. I'm not a mathematician. I don't claim to be a mathematician. I didn't pass the bar, but I know a little bit. And then that's kind of enough for me to get forward within these things and progress them. And then all of it's not just one field that is successful with an AI, right? It's not just being the best mathematician in the world or the best computer scientist, etc. It's that blend and that jack of all trades. And then that's where I shine overall is the across the boardness of that. And then so just highlighting, pointing these things out, I'll leave a link to this particular research paper, a mean field theory of data expectations. If you like this type of content, please like and subscribe. Thank you very much.